Nucleophilic attack on a carbonyl followed by protonation is a 1,2 addition process. If the carbonyl is conjugated to an alkene, a second mode of addition is possible, where the nucleophile adds to the beta carbon to give a 1,4 or conjugate addition. Simple resonance structures reveal why nucleophiles can add to the beta carbon of an enone. In terms of molecular orbital theory, the LUMO at the beta position is large and overlaps more effectively with the HOMO of the nucleophile. Thus, the complete mechanism of this process is attack of the nucleophile at the beta carbon, formation of an enolate, and then protonation of the enolate at C-alpha to give a 1,4 addition product. For example, the nucleophile could be negatively charged, as in this thiolate, or it could be a neutral nucleophile like pyrrolidine, adding to a cyclic enone. Any good electron withdrawing group on an alkene will facilitate this process, like a nitro group. Two ester groups on an alkene will make it easily electrophilic enough for these reactions. The electron withdrawing group could be an amide or a nitrile. Enzymes can direct conjugate additions, like that of ammonia to this alkene, to give a beta-methyl aspartic acid derivative. Fumarase directs 1,4 conjugate addition of water to fumaric acid to give the hydroxy diacid shown. Conjugate additions can also be reversible. If a cysteine residue, for instance on an enzyme, were to add to a Z double bond, rotation around a sigma bond, then reverse 1,4 conjugate addition could give the E isomer of the starting material. So, yabba dabba do. That's it for enzyme-mediated reactions. Let's look at some intramolecular aldol reactions facilitated by conjugate additions. Conjugate additions of enolates to enols and enones generate an enolate. This enolate may transfer a proton to give another enolate, which can then intramolecularly add in an aldol reaction to form ring system. The hardest step to understand in this reaction might be why one enolate would exchange to give another. But of course that's a thermodynamic consideration governed by the ring size which forms. This is a very good reaction to form fused ring systems like this 6,6 ring system or this 6,5 ring system found in steroids. The addition of hydrogen peroxide anion to enones, another electron-deficient alkene. The conjugate addition product is an enolate which returns to displace OH by breaking the weak O-O bond, forming an epoxide. In this example featuring a sulfone, it doesn't matter which stereochemistry of the alkene we start with, so ring closure gives the thermodynamically preferred trans epoxide. Electron-deficient alkenes with a leaving group on the beta carbon where the nucleophile adds can form enols or enolates to reform the double bond, but with functionality at the beta position. Rings form via two conjugate additions if there are two leaving groups. Bromination of enones gives a bromine addition product. If that is treated with base, an enolate can form, and that enolate can collapse with expulsion of bromide from the beta position. This gives an alpha brominated enone. Those reactions are an excellent segue to nucleophilic aromatic substitutions. These feature addition of a nucleophile to a carbon that's substituted with the leaving group on an aromatic ring. In a slow step, a tetrahedral intermediate is formed, and this collapses with displacement of the leaving group to give a substituted aryl system. Electron-deficient alkenes that can place the negative charge on an electronegative atom react fastest in these reactions. Ciao!